Good afternoon, everyone. My name is Austin Crow, and with my partner Victor Corja, we will be looking into the possibilities of decreasing noise interference in spatial audio. Spatial audio is a vital component of immersive media for both augmented and fully virtual reality, and allows the users to experience sounds in 3 dimensions. Generally, this refers to headphones or some format of head-mounted display. Taking into account directional sound when projecting audio to the user, but can also be implemented in greater spaces such as surround sound technology in home theaters. The general purpose of our project will be to remove noisy interference from noisy spatial audio data, which would provide a significant boost to the immersion of users of AR, IR, and VR systems. Additionally, while there are already some existing systems for cleaning noisy data, we will attempt to provide a model capable of detecting and removing both low-level, constant noise, and sudden interferences or interruptions, which is uncommon implementation for noise cleaning. Spatial audio, also referred to as immersive audio, has received a lot of attention over the last decade with the advent of new applications for immersive media such as virtual education platforms, urban soundscaping, and audio therapy. Spatial audio is not a purely virtual or digital concept. For example, the best concert halls are designed in a way to amplify orchestral audio in such a manner to ensure that the audience is surrounded by sound. The alternative is an experience where the orchestra seems distant, in many ways similar to simply listening to a recording of the experience. The inclusion of smart sensors, machine learning, and AI in many new immersive media technologies has allowed reality augmentation services to significantly heighten the user experience. However, while the technology for provisioning spatial audio exists and has been extensively researched, the use of noisy data for such a case could cause noticeable issues. Many headsets are designed in a way to support spatial audio, and because of this, both audio and noise is amplified. The goal of spatial audio is to reproduce a natural listening environment as closely as possible, whether with real sound data, augmented, or custom sounds processed to fill a user's virtual auditory space. Conventional systems use 5.1 and 7.1 surround sound setups. Both of these involve a set of speakers. In the case of 5.1 system, this is 5 speakers and a subwoofer, and for the 7.1 system, this is 7 speakers and a subwoofer. As shown on screen, setups generally consist of speakers located around the user, spaced at locations which have been found to be a key in audio perception, with a subwoofer placed anywhere in the system to simulate low-frequency audio signals. Newer setups might consist of 5.1.2 or 7.1.4 surround sound, which includes an additional 2 or 4 speakers respectively, located at an increased elevation, such as ceiling speakers. The addition of height information, while coming at a significant computational complexity and financial cost, can distinctly augment user experience and immersion.
When describing an immersive audio system, there are generally 3 types of audio involved: channel-based, object-based, and scene-based audio. The first type, channel-based audio, generally uses a digital audio workstation, or DAW, to mix sound sources into a channel-based mix for different layouts with target speakers. This leads to a very straightforward setup, where a certain audio signal is pre-made specifically for one speaker, although it can lead to some issues when the original sound data does not match the format required for the target layout. In cases such as these, the DAW can be used to upmix the audio, which adds new artificial signals to pad out the missing signal arrays, or downmix the audio, bringing it down from a larger number of channels to a smaller one by consolidating various signals. The next category of spatial audio is object-based, splitting audio signals into metadata-based objects, with each particular signal representing a distinct audio asset. This can be most easily observed within immersive games, where some in-game object is attached to metadata containing a certain set of sounds and correlated with a Cartesian map representing that object's proximity to the user. This allows for very customizable signals, such as the creaking of a door in proximity to the user, with the signal's volume being dependent on the actual proximity. The actual location of the object can also be approximated with sound based on sensory perception theory, and the use of multiple speakers to create the illusion that a sound's origin point, or location of the loudest signal, is in a particular point with relation to the user. Systems which implement object-based audio often use the azimuth, which is an angle within a spherical coordinate system formed between an observer and some object located at a particular horizontal and vertical perpendicularity to the user. Scene-based audio is the last common type of surround sound, and is based on the higher order ambisonic, or HOA, technique. This technique is the least common in current implementation, due to the general preference for the experiences generated by the other two categories, but it uses a similar approach to object-based audio. Rather than using specific objects, scene-based audio splits an audio signal into 4 channels: W, X, Y, and Z. The first channel, W, contains omnidirectional information, a zero-order signal that is projected through all emitters or speakers. The other 3 channels, X, Y, and Z, each represent not a specific channel, but rather a set of informational algorithms for each axis. This is used by a set of speakers to generate the audio based on the speaker's azimuth. The location of the speaker relative to the user is taken into account to generate a signal based on the angle with respect to each of the axes, and the result is then projected. Scene-based audio is very useful for systems where maneuverability is important, since it can be easily rotated, mirrored, or otherwise manipulated by only modifying the speaker's angle. Technically, all projected audio is channel-based, since the output is dependent on the number of signals created in the final audio output. If one considers listening to an older car radio, the output is coming from a single speaker, meaning that it is definitively mono-channel. However, audio can be mono-channel even if it is played through multiple inputs, as long as the same audio signals are transmitted to all speakers within the system. Another very common setup between mono and surround channel systems is a stereo system, which involves 2 distinct signals being played through outputs. This is most common for headphones, where each ear receives one part of the signal to enhance immersion. The last common setup is the surround sound system discussed up till now, which has a multitude of signals surrounding the observer, providing the greatest immersion out of the 3 techniques. Note that it is not necessary to have a lot of speakers or outputs to play spatial audio. With advances in technology, dual speaker systems, like Apple's AirPods, can play spatial audio by digitally altering particular signals within the audio to mimic a more distant or differently placed origin from other signals. This is accomplished by audio filtering to account for the human auditory system structure, and provides exciting new possibilities in the future of digital audio modification and immersion.
While there is a large body of work on noise reduction in stereo audio, the research into the same field for spatial audio is far more sparse, simply due to the relative novelty of the technology's digital implementation. In some existing work, the focus has shifted more from the technical perspective of noise suppression to a psychological evaluation of human auditory perception, and ideas of how best to mimic real-life spatial audio with doctored data. Other researchers attempted to extract only specific portions of audio, such as speech data, without retaining the rest of the signals, resulting in a heavily lossy model. Even within noise reduction models for stereo audio, there are some limitations within current technologies, which could be addressed by the approaches we are proposing and considering. For example, while many models deal with separating noise data from desirable data, they often conflict as to the definition of noise, using specific auditory thresholds to distinguish between viable and non-viable cues. An example of this is the cleaning of a recorded speech on a city street. Many models would be able to reduce the background noise of wind or sounds of a passerby, but the majority would retain sudden interferences such as a car honking or a police siren. Interferences to spatial audio can not only cause a loss of immersion, they can cause significant pain and discomfort, and in some cases even cause damage to the user's hearing, given prolonged or often repeated disturbances. Our goal is to develop a model capable of diminishing both general noise and sudden interferences within spatial data. Having such a model would be extremely beneficial in many industries, such as journalism, filmmaking, and gaming, among many more. And depending on the implementation, could be an advancement not only for the field of spatial audio, but also for that of stereo audio.
Our idea is to use existing models and architectures that have been proven to provide noise cancellation or reduction and combine them in such a way that they satisfy the criteria we provided in our goal. Additionally, we would have to write custom code to allow the model to handle spatial audio with a variety of compositions, including both the audio basis, such as channel or object, and the multitude of channel compositions, from 1 up to 10 and potentially above. The specific techniques we are going to implement will include a wavenet, convolutional dilation, and auditory decorrelation. These techniques are commonly used with standard monosound audio for removing signal interference, and while the combination of wavenet and decorrelation is not usually employed, these techniques will enable our model to handle both low-level noise and sporadic interference. The process of obtaining data for our research will be vital to the success of our project, since high-quality datasets with both clean and noisy spatial audio are difficult to come by, especially if a specific format is necessary for model operation. The requirement to support multi-channel and multi-format audio and account for multiple types of noise means that the data we use will have to be both significantly multimodal and diverse, and would allow us to test the variety of use cases desired. This consideration may require the fabrication of spatial audio using a digital audio workstation to provide data capable of mimicking multi-channel signals. The various component tracks of spatial audio will be run through our model, and a recursive process would continuously diminish the level of noise persisting within the data sample. This would allow us to identify the ideal number of recursions required to generate audio clean enough to understand, yet retaining enough data for complete clarity. Additionally, we would be able to test our model both with the initial input being provided in separate tracks, and with a single composite track being provided and being divided into components post-cleaning. While our idea consists of several potential solutions, which will be selected based on experimental results, any of the chosen configurations would serve the desired purpose, and the experimentation is simply an additional step to attempt to optimize the proposed system. The model we obtained through our research and testing would be set up with the most efficient settings for removing noise of both mentioned kinds from spatial audio data, and would enable the potential extension of adding a machine learning wrapper model, which would derive the ideal settings based on the kind of provided data.
WaveNet is one of the leading technologies in audio synthesis and is becoming the standard in the field. Due to this, the WaveNet approach will likely be one of the main focuses regarding the system architecture for our project. For our background on what WaveNet is and how it works, WaveNet is a deep neural network that is primarily used for generating audio from raw audio. This being said, WaveNet has also been adopted for generating images by unconventional means, such as focusing on color channels, as well as being used for stock price prediction. By using an autoregressive model, WaveNet is able to apply deep learning strategies to longitudinal data, which put more simply, means by taking previous time series data points, it will be able to determine the probability of what will come next. Due to the use of raw waveforms, WaveNet can be tailored to just about any audio-related problem or project. A great example of something that uses WaveNet would be the Google Assistant voices. Google adopted the use of WaveNet as they wanted their voice to be more human-like and be able to easily adapt to different dialects and languages. The nature of sound quality makes ranking audio techniques rather difficult as it's primarily opinion-based. As a result, the mean opinion score is what's used, and WaveNet consistently beats out the other methodologies. The figure that is shown is an example of what a traditional WaveNet architecture would look like. A key point in a WaveNet architecture is that the input layer affects each of the subsequent layers. In this example, the architecture has an input layer, 3 hidden layers, and a final output layer, totaling to 5 layers. And each of the inputs affect a total of 5 different outputs. This trend is no coincidence. For as many layers there will be that many outputs that the input will have a direct connection with. While this is very good for accurate audio synthesis, it is very costly for a computer's resources, due to the heavy cost of a dilated convolution is used, and we will talk more about that in the following slide.
The primary goal of dilated convolutions is to allow inputs to have a large receptive field with a lower number of layers. thereby enabling accurate synthesis with a fraction of the computational resources required for a standard wavenet. This technique is similar to a pooling or striding layer commonly used in a traditional convolutional neural network. What the dilation does is essentially skip over input values in certain layers in order to have that input reach an output node that would normally be far outside of its reach. The computational efficiency is much greater due to this technique, and inputs can increase the receptive field by stacking these dilated convolutions. This graphic is a visualization of how the dilated convolutions work. As you can see, the architecture is almost identical to the wavenet showed previously. However, the major difference is that the inputs that would normally touch every node above, and the next one, is now a pattern corresponding to the level of dilation. For example, this dilation pattern is 1, 2, 4, 8, essentially just doubling every time, thus letting the very first input affect the 16th output, as opposed to the original wavenet that would only get as far as the 5th output. If this were to be a standard wavenet, in order to reach the same output node, the wavenet would need 16 layers. The number of dilations shown under each of the layers represents to how far the previous node traveled. In the second to last layer, the node traveled 8 spots to the right, and this can be seen in the output layer's dilation of 8. Also, each node affects all the nodes leading to the last layer, as shown in the far right of the graphic, with the node going directly up. Like previously mentioned, stacking these blocks gives an even greater ability to increase the receptive field.
Sudden noise and interruptions are a major factor when looking at the ability to understand auditory information. These sudden interruptions or apparent jumps in high-frequency audio are often referred to as speckle noise. There are a few different ways to deal with speckle noise when referring to audio, the most common being determining a noise level and removing any audio that surpasses that determined level. However, all audio signals are not made equal in regard to the strength of the audio. A set determined level will not be able to apply to all cases, primarily when looking at weak signals. To counteract this, a variable noise level can be used that is adjusted based on the strength of the audio signal. Along with the determined noise level, decorrelation is used based on a linear prediction model to detect the location of the interrupts. Decorrelation is essentially determining what sections have speckled noise and singling those sections out. After this decorrelation, we can look at the kurtosis to help further narrow down what will actually be removed from the audio. Kurtosis just means the highest point on the frequency. The way the interpolator works is by first going through the decorrelation, then frames the signal into sections, finds average energy measure and kurtosis measure, threads them locating the noise, replaces the distorted samples, and finally outputs the noise removed speech. Our estimated timeline from today's presentation of our project proposal until the end of the semester and the final presentation is currently planned as follows. Upon settling on a set of results we want to obtain through our research and experimentation, we will identify a dataset which we can use for both training and testing our model, if both of those steps are required. Depending on the particular model and technologies we use, it is possible that a pre-trained model, or one not using machine learning, would prevent the necessity of splitting a dataset into training and test segments. The process of finding and selecting a dataset will also be quite complex, since there will be several factors to consider, largely based on the availability of the data and the formats we would need. For example, if there is already a dataset in the correct surround sound format with both noisy and clean data, we would still need to consider its applicability to the selected approaches. However, if such a dataset were to prove difficult to obtain, we would consider using a dataset of stereo audio with both clean and noisy data, and convert it into multi-channel binaural dataset using some existing models or applications. Both of these approaches have their merits, with the first offering far more convenience, but the second giving more customizability of the data and a greater level of control and validation potential.
Having decided on both an approach and a dataset, we would then begin constructing our model and experimenting with the goal of obtaining initial results around the end of March, with the aim of finalizing the model, comparing its efficacy against other models, and otherwise validating its capabilities by the middle of April. The final 2 to 3 weeks we'd be devoted to summarizing our efforts and accomplishments over the course of the semester in a presentation. On this slide, you can see the references we used to develop this presentation.